I wanted to finish up on TrueBit in this lecture. So we discussed last time how TrueBit works, and we said that first a solver is going to submit two solutions, right? And then what he's going to do is he's going to point to one of those solutions depending on what the random bit the system provides. Okay, and only he knows that random bit because it consists of some information private to him, right? And then we have a challenge time in which anybody can challenge the solution proposed by the solver, right? And then finally the bit is revealed, right? So we said first of all, maybe just let's have a recap. So we said that in case there is a challenge, what can be done is there is a game in which what I'm showing here on this axis is the number of execution steps. Let's say that T is the last execution step, and we do a binary search and we find the first place where actually the solver and the verifier disagree. So they disagree on the state, and then what the what the miners have to do is they look at this E-1 where both had the same state, and they execute the instruction to go to this next state, right? And so using that, they're able to find out who was right and who was wrong, right? So the question is, how do we reward people? And it turns out that that's quite tricky, and we'll have to look at various cases. So first of all, let's assume that the bit is true. Right, and so how do we decide whether the bit is true? We said essentially we are going to look at hash of block hash. This is the block at a particular location in the blockchain, right? So after the solver has put a commitment, so he puts a hash of his random bits on the blockchain. So this is a commitment. This is put on the blockchain. So he doesn't know the bit as yet. So the block after this is put on the blockchain, we take the hash of that, okay? And we are going to concatenate R to it. And this is going to be used to decide what the bit is or not. So if it is, let's say, less than the threshold, some threshold, then let's say that it is bit is equal to false, okay? And this means that it is a forced error. Okay, and so let's say that the solver has to point to SF. Okay. And of course, if it is greater than threshold, greater than or equal to the threshold, then we say that the bit is true. Okay. So he is supposed to point to his correct solution which he had put on the blockchain. Yeah, so let's look at the case where the bit is true. Okay. So now what happens? So there are different cases. So suppose there is no challenger. Okay. Now in this case, since there is a no challenger, we assume that the solver is correct and he gets the full reward. Solver gets, let's say, the transaction fee. Okay. And in case there is a challenge, then we have to think what to do. So one or more challenger. So here it's tricky. What are we going to do? And we'll have to play some game like this, right? Like we said that we're going to take the challenger one by one and we're going to have a competition with the solver, and we are going to find out which was right. I mean, who's going to win this game, right? So suppose the solver goes correctly from e minus 1 to e, then he wins, right? But if the verifier goes from e minus 1 to e, then the verifier wins. So now what we have to do is we have to play the binary search game. With the challengers one after the other. And let's look at this. So suppose the solver defeats all the challengers. Then of course the solver gets the entire transaction fee. So we assume that the solver is right over here, since none of the challengers was able to beat him. Plus he should get, we need to penalize the challengers so that he gets half the deposit of all the challengers. So clearly this is going to take a lot of time. I mean, suppose there are 100 challengers, let's say, we have to play this binary search game. Of course, it could be done simultaneously, that you can have a solver and challenger 1, let's say, playing this game at the same time as solver and challenger 2. Right? That could happen, but it would take up a lot of transaction space on the blockchain, because we are using the blockchain as a whiteboard in which they have to compete with each other. Okay. So what about the other case where some challenger defeats the solver? Okay, so till now the solver has won, which means and he's got the transaction fee, which means the transaction has been executed, right? But now the solver has been defeated, and the question is, what do we do now? Should we assume that the challenger who defeated him was correct, and should we take that person's solution as the correct one? So that's not what TrueBit is going to do. So suppose, let's say this is the execution trace like we saw above. And let's say we said that we found that the solver state is wrong at this place, right? So and this is the challenger. So the challenger won the competition over here. Okay, we said we did a binary search, and then we found that this was where they first disagreed. And when we went from E-1 to E, we found that the solver was wrong, but the challenger was correct. Okay? But that, suppose we give the benefit of the doubt to the challenger and we say that this is correct, this solution is correct. The problem is, like, maybe he has made a mistake over here, right? Made a mistake or deliberately done something wrong. So his final solution may be wrong. So we are, at least in this particular case, the TrueBit system is not confident that this challenger is correct, right? So what we are going to do is we are going to refund the task giver. So the task giver is the person who gave this computationally intensive transaction on the blockchain. So the task giver gets a refund. Of his transaction fee. Right? And he has to resubmit the transaction again if he wants it solved. So of course there may be some way to optimize this. Maybe he doesn't have to resubmit the whole CIT because it's already there on the blockchain, and maybe he puts a new transaction fee, let's say and he says that I would like you to re-execute that old transaction which I put on the blockchain, right? So in this case the solver has lost, and so we are, if the solver has correctly executed this whole thing, then we can show that this will never happen to him. If he's correctly executed, then for whatever this E-1 is, whatever he submits here will actually be correct. Okay. So we don't have to worry about that. So if he's got this wrong, I mean if he lost this game, that means he's definitely wrong, and in which case we have to punish him, right? So the solver loses his deposit, and what happens here? So we give half to the challenger who defeated him, and the other half we give to the we distribute let's say it's split between the task giver, because he's wasted the time of the task giver, right? So the task giver deserves some compensation, and part of it goes to the jackpot. So this jackpot is just, you can think, a collection of which is there on the blockchain, which money is collected over time in this jackpot. Okay, so this can be distributed when we have the bit to be false, and we look at how that is done. Of course, there are other ways to which where we could contribute to this jackpot. So, for example, when somebody submits a transaction, maybe a tiny part of it can be taken as a tax for this jackpot. Right? So the jackpot builds up over time, right? And this jackpot is to be paid out in case the bit is false. Okay. So you might think, what if we gave everything to the challenger? You know, what if we didn't put something in the jackpot, for example? Okay, so so the thing is, whatever we do might open up some sort of an attack. So suppose we gave 100% of the solver's deposit to the challenger who won, right? Then what the solver might do is that he could himself be the challenger, right? We don't know, this is a permissionless system, so we don't know who's the challenger and who's the solver. So the solver is himself the challenger, then he doesn't lose anything. But this way you ensure that even if the solver is the challenger, he gets back only half his deposit, right? And even if he happens to be the task giver in that rare case, he won't get back 100% of what he actually deposited. Okay, so this is an incentive for the solver to actually behave himself and do the calculation correctly. So what happens when the bit is false? And this is where it becomes interesting. Okay. So this means that the solver points to the false solution, the fake solution which he put on the blockchain. So the solver points to SF. Okay. Now what should we do? And in this case the solver is given nothing. And why is this done? Well, because solver knows what the bit is. He knows before anybody else, before the challengers come into the picture. The solver knows that the bit is false. So the solver is expected to be a challenger. Okay, so that's not a problem. He can always challenge himself and get some reward. Right? So he's behaved honestly. He submitted a correct ST solution but a false SF solution. But it so happened he was unlucky and the bit was false, but he can still earn a little bit of money. Now what should we do with the other people? So there are lots of other people who have challenged, and so what we are going to do is we are going to distribute the jackpot among them. So among all the challengers. Okay. So suppose there is a certain amount of jackpot over there. Okay, and of course TrueBit is more careful about this. So the whole jackpot is not distributed among these people, because there are many different CITs being executed, let's say. So let's say a small amount, depending on the computation, let's say this is the, let's say that we call the total jackpot, let's say JT, right? Let's say this is the total jackpot. So there may be many different CITs running and so on, and so we don't want to exhaust, get rid of the full jackpot just and distribute it among these challengers. Some part of it is chosen as the jackpot for this particular CIT, right? Depending on the computation involved in that transaction and so on, right? But this is just a fine detail, but let's say that this amount J we are willing to distribute among these challengers. Okay? So this is very, very important for us to give this incentive, because challengers need to know that they will earn some money once in a while, right? Maybe most of the time the bit is true, so they get nothing. Even if they do the computation, the computation put by the solver is correct, so they don't get anything. But once in a while the solution is, the bit is false, in which case they can expect to get some reward. Okay. So they distribute the jackpot J among all the challengers, but now you might see that there's a problem over here. Somebody can perform an attack, even the solver himself, right? He sees that the bit is false, so he wants a bigger reward. Right, and he knows that it's going to be equally divided among all the challengers. So he is going to perform like a Sybil attack. He's going to claim that he is, let's say, many different many different challengers, and he's going to get a higher reward. Okay. So suppose, let's say, reward for a single challenger when there are n total challengers is J divided by n. Here there's a problem. Then any challenger might could pretend to be, let's say, suppose he has more than one deposit, right? He can volunteer to be another challenger, right? So what he can do is he can let's say challenge many times. So he gets a higher reward. Okay, so if somebody challenges more times, then he gets a higher reward. Okay, and of course, it's not trivial to do this, because we said to be a challenger, you have to put a deposit. So somebody might have, if he wants to have multiple challenges, he'll also have to put multiple deposits, right? So this is not arbitrarily scalable, okay, but and that deposit sort of has some Sybil resistance, right? That you can't arbitrarily say that you're any number of parties and challenge. But you can have a sort of problem if some sort of a cartel is formed. So out of all the people who are potential challengers, right, maybe many of them form a group, and somebody says that I'm going to be the one who will do the challenge, you guys can just relax, you don't have to do the computation, and I'm going to do it myself, and then you just sort of repeat whatever I challenge, right? So they can form a cartel among the people who have who are potential challengers. Let's say potential challengers. Gang up, and only one does the computation. And others, let's say, just reproduce the same challenge as this person. Okay, so even though there are this many challenges, the thing is there's only one person doing the computation. So let's look at a particular attack where which can be exploited in case the jackpot is divided equally among all the people who challenge. So suppose a set of people who are potential challengers form a cartel, and let's say that these are the various challengers, and let's say that there are n of them who are going to challenge, right? And normally you would expect each of these people to do the computation, right? So they put in some particular computational effort and they get some reward, and there may be some other potential challengers let's say that there's a large pool of them, and only these challenge. Only the first n challenge, right? Now some of these are going to collude. Let's say that the first m of these, they form a cartel, right? And they agree that only one of them will do the computation and the others will repeat the same challenge, right? And they will also be challengers. Now these people have effectively become lazy challengers, right? They don't do the computation, only the first one does the computation, right? So they have an advantage over the others, because effectively they are getting the same reward as others, but without doing the computation. They are saving on computational effort, right? These people, of course, are honest, and because they don't do the computation, they don't get any reward. Okay, so these other people, let's say that there are n minus m over here, they are together actually doing the computation n minus m times, right? Whereas these people are doing less. So they have a slight advantage. Okay, I mean, so for example, these people, let's say each miner has to take one server, for example, on Amazon, let's say, right, in order to do the computation. Normally they would have had to let's say rent out m different servers to do the computation, whereas here they do it only once, and so effectively they are earning more than the others. Okay, so how do we handle this problem of a cartel? So suppose you have an entity who is one of let's say n people who want to challenge, and let's say initially these n people are all different, right? And so what we want to do is we want to come up with a scheme to distribute the money, so that if this person pretends to be a second one and he sort of gives his challenge twice, then he will actually end up earning less money than if he was a single person who was actually putting the challenge on the blockchain. Okay. So how are we going to do this? So suppose he was a single person, that there were only n entities, but suppose he actually pretended to be two different people, then totally you would have had n plus 1 challenges. So we want him in this case to earn less money than if he was only submitting one challenge. Okay, so how are we going to do that? So we are going to generalize. So suppose an entity submits k challenges for k greater than or equal to 1, right? And what we want is that if he submits k plus 1 challenges, he earns less. So let's think about it. So suppose the suppose the reward to be split up with let's say with n challengers is Jn. Okay, so previously we were saying there is some total amount J which we are dividing among the n. Now let's make that a function of n, and we are going to call it Jn. Okay, and you can imagine that what we are going to do is we are going to reduce this Jn drastically as n increases, so that in order to dissuade somebody from submitting his challenge multiple times. Okay, so but what should this be? So suppose there are n challenges initially, let's say this is out of total n challenges, right? And so when he submits yet another challenge, it's going to become n plus 1. Okay, so what I showed over here is the situation when k is equal to 1. Okay, but I'm generalizing it for any k. So what we want is that is reward. So what is his reward initially? So when there are n challenges, he's going to get k out of n. Right? We obviously have to divide this reward equally among n people who have challenged. Okay, and this we want larger than when he submits yet another challenge. Okay, but of course, if there are n challenges, we are going to distribute only jn plus 1. Okay, and this is clearly we want this to be something less than this. Okay, so what do we end up with? Jn plus 1 is less than n plus 1 divided by n multiplied by k plus 1 times jn. Okay. So what do we want over here? So this quantity is greater than 1 and this quantity is going to be greater than or equal to half for all values of k, right? And so this quantity totally is going to be greater than or equal to half. I should say greater than half, right? Okay. So what we are going to do is we are going to set Jn is equal to the J there, which is the total jackpot, which is, let's say, set aside for this this particular CIT, right? This divided by 2 to the power of n minus 1. Okay, and we can see that in fact this is going to be true because this number is going to be greater than half. So if we actually divide by 2 every time we go from n to n plus 1, this quantity on the left side is going to be less than the quantity on the right hand side. Okay, so what what does this mean? Of course, if there is only one person challenging, then we're going to distribute the total amount j to among the challengers. But if there are more people, n is greater than 1, then the amount distributed is going to be decrease exponentially, right? So each challenger gets Jn by n reward and not j by n, right? So that is effectively going to be equal to this. It's j divided by n times 2 to the power of n minus 1. So it's quite a tricky solution, I should say, that if the more and more challengers you have, the more you decrease the total amount which you're going to split up among them. So this particular scheme is going to disincentivize anybody from submitting multiple challenges. Okay, and it solves these issues of cartels and so on. Okay, but there are other issues which can come up. Suppose, for example, somebody is a Byzantine adversary. So if a person is a rational miner, so let's say that, I shouldn't say miner, but a rational adversary. So rational adversary wants to maximize his earnings. And so if for a rational adversary and with this scheme, he is not going to submit multiple challenges, right? But a Byzantine adversary doesn't care about losing money. Okay. So is this scheme going to work in this case? Right? So rational one wants to maximize earnings. So this is indeed very tricky. So suppose somebody has a lot of money and he doesn't mind losing the money. then how can he beat the system? So then there is an attack possible over here that he doesn't mind submitting the challenge many times because he's a rich person. So what he's going to do is he's going to submit lots of solutions so that this total amount goes down. So there's an attack possible. So he submits many solutions. So what happens is that the n value goes up, the total number of solutions goes up, which in turn leads to the amount which is split among them becoming small. And this is a big problem because now other miners who are honest will not be getting much. They are going to submit only one solution because let's say they are rational. And this Jn goes down exponentially as n increases. So this is a problem. Jn becomes small, and so honest people get very little. So they will be disincentivized from actually challenging at all. So somebody puts in some deposit and tries to challenge, but then he realizes that he's not earning anything because maybe there's some other person who is submitting lots of solutions and decreasing the value of it. So this actually disincentivizes honest people from challenging, so they may stop challenging at all completely. Now this is a problem because if they stop challenging, then all the honest people drop out, or even the rational people will just drop out, and the only person who will be left challenging is this Byzantine adversary. And that's a problem. If he's Byzantine and he's the only one challenging, then he might actually also masquerade as a solver and submit wrong solutions and then not challenge himself. Right? And so this is a problem. Only the adversary remains. And he can pretty much do anything with the system. He can submit wrong solutions, not challenge or whatever. So TrueBit is extremely complicated, but because it's so complicated, it has lots of attack surfaces. In fact, in the paper which I have uploaded on Moodle, you can actually see that they look at many different things. What if the task giver colludes with the solver? Or what if the solver colludes with a verifier, right? What if, challengers, what if the challengers form a cartel, right? So many different things can be done, and they look at each of them and try to come up with answers, right? But given this split of the jackpot money where the total amount spent decreases exponentially with the number of challenges, it's very easy to see that it will not survive a Byzantine adversary. Okay? So what we do in Yoda is we come up with a different scheme. And it's not essentially what we're going to do is instead of coming up with a single solver, we're going to come up with a committee, and we're going to have a different threat model. We're going to assume that most of the people in the committee are going to be honest. Okay, the Byzantine people are in a smaller fraction, but while we try to do some optimization, it becomes very, very tricky, right? So TrueBit is probably going to work for a rational if all the people who are challengers and solvers and so on are rational. Okay, at least I don't see a very clear loophole, but there might be because it's a very complicated system. But when you have a Byzantine adversary, it's definitely going to fail. Okay, so in the next lecture, we'll start talking about Yoda.